What's up guys, Andy here. We are diving together into day 3 of the From Zero to Hero challenge, and I've prepared for you an awesome problem which actually has a smart solution which uses my favorite ever data structures, a very simple one but super powerful. First of all, if you really like these videos and want more, make sure you stay tuned by clicking the subscribe button, make sure you like the videos and support this channel. Your job is to make it happen. As always, my job is to make it awesome. So, let's read the statement together. The problem is called 132 pattern, and given a sequence of n integers a1, a2, an, what is a 132 pattern? A 132 pattern is a subsequence ai, aj and ak, right? So three numbers from the array where I is less than j, j is less than k, and a of I is less than a of k, which is less than a of j, right? So the first number ai is the smallest one, then the second smallest number is ak, right? And then the biggest number from these three is the second one. That's why 132 pattern, right? So design an algorithm that takes a list of n numbers as input and checks whether there is a 132 pattern in the list. Awesome. Let's just open our notepad as always and take the first example. So example number 1 is 1, 2, 3, 4, right? So obvious we don't have three numbers to satisfy that because the array is increasingly sorted. But now for 3, 1, 4, 2, we shall return true because the 132 pattern, what is it? Is 3, 4, 2 or 1, 4, 2, right? This is good. So 3, 4, 2 or maybe 1, 4, 2, right? The first element is the smallest one, then is the third one, right? Is the second smallest one, and then the second one from this is the biggest one. So let's start thinking about this problem. And as always guys, you probably, if you watched my last videos, you probably got used to it. We always start by brute force approaches, right? So I want the worst brute force approach ever, and that is big O of n cube. So let's start by this. Brute force number 1, right? Brute force number 1, which is big O of n cube. What shall I do? I should fix each number, right? So make a for loop for I, make another for loop for j, make another for loop for k, right? So fix each of those. Fix I, fix j, fix k, check if they are valid, so a of I is less than a of k is less than a of j. If it is, return true. If not, continue checking. In the end, if you haven't found a solution, you obviously return false. So, alright, this is super simple. Let's try to find another brute force, which now to be n squared. So brute force number 2, I want something in big O of n squared. And let's be smart about it, right? For big O of n cube, we could fix all those three positions, I, j and k. Now for big O of n squared, we won't fix all the three of them. We are going to fix only two of them. And which ones should we fix? Well, I don't think it matters at all. So I am going to fix, let's say, fix k and j, right? So the last two of them, right? When I fix k and j, right? So it's actually j and k. This is the order, right? So fixing j and k, and I should check if, so check if ak is less than aj, first of all, right? And if it is, I should find the missing I. And what should I do? I should see if there is an I which is less than j, such as, so check if there is some I, right, which is less than j, right? And what should be the property of ai? Obviously it's less than ak. So and ai is less than ak. But how should I check this? I should check this in constant time, right? So on big O of 1. So I want you to imagine right now, we have fixed j and k, right? And we have seen that a of j is bigger than a of k. And now, what we want here is to find some I less than j, such as a of I is less than a of k. So, the question is, do I have an element from position 1 to position j minus 1 which has a value less than some given value, which is obviously ak? So if I have to try to find an element from some range less than other value, the perfect candidate for that is going to be the minimum element from that range, right? So it doesn't make any sense to check the greatest element from position 1 to position j minus 1 when I can check the smallest one, because the smallest one has the higher odds to be less than a of k. So this is smart, alright? So what I should basically do in order to check this in constant time is that I should know the minimum value from some prefix very quick. And how do we know some value very quick? In big O of 1? Exactly, pre-computing it. So we shall have another array. We shall have, let's say, mean val, right? We should have an auxiliary array, which is mean val of I, which is going to have the minimum value, right? Between the minimum value between a1, a2, dot dot dot, ai, right? So the minimum value of this prefix. Now, if I pre-compute this array, which is obviously linear time to pre-compute, right? It's like the partial sums, but it's basically now a partial minimum. After I compute this array, I will know my information in constant time, which is awesome, right? So, mean val of I is basically the minimum between mean val of I minus 1, so the minimum between the first I minus 1 elements and now my current element, which is ai, right? All of this in a for loop. So for I is going to be from position 1, let's say, all the way to position n at I++, I will have the mean val. After computing this, after pre-computing the mean val, I should fix j and k with two nested for loops, and I should check if a of k is less than a of j, and most important, the mean val of j minus 1 is how? Is less than a of k. And if it is, we shall return true right away. If not, after executing these two nested for loops, we know that we won't have a solution, so we return false. Perfect, guys. So this is the second brute force approach, big O of n squared. Now, let's dive into the optimal solution, which is linear time, right? So optimal solution is going to be pretty amazing, actually. It's big O of n. So I want you to pause this video right now and think about the optimal solution, because obviously we haven't gone through these brute force approaches because they are useless, right? So the brute force approach number 2 will help you, will be the foundation to find your optimal solution. Pause the video and think about it. Perfect, guys. I hope as many as you got the optimal solution right. It's not an easy one, it's quite tricky, but it's super awesome. And we are going to dive into my favorite data structure, which is the most basic one, the stack. This problem is going to use the stack to be solved. But now, this is my hint. If you want to think again of the problem knowing that it's solved with stack, be my guest, and we are going to take this step by step. So, in the brute force approach number 2, we have fixed j and k, and found that our favorite a, the most favorable candidate, is the minimum value from the prefix from position 1 to j minus 1, right? Great. Now, for big O of n, I'm not able anymore to fix j and k. So I should fix only one of those. And I am going to share with you a super powerful trick which is used in 99% of these kinds of problems. When you have to find or fix 3 pointers, I, j, and k, right? But because of the time complexity, you could only fix one of those, you always fix the middle one, right? So it is the most useful to fix j here. So I am making a for loop for only fixing j. Now, let's take a look again at the brute force approach number 2. And remember that when we fix j and k, we know that I, right, that minimum value, that's our I. This still holds. Now I don't know the k. K could be everything between j plus 1 and n, but I, still the most favorable I, is going to be the minimum element from that prefix. So I fix the j, I know what is the I, right? So I is the position of mean val, basically, of j minus 1, right? And now I should find if there is a k. So we should check in constant time if there is some k, such as, well, first of all, after I find my I, I should check if I and j are values, right? So obviously what we know here is that ai should be less than aj, right? So first of all we check this, check if, right? And if this holds, perfect, we should go on and find the k if there is one. So check if there is some k such as this k should be between these values, right? So this k should be less than aj but should be greater than ai, right? Well, remember that I have fixed my j and I know my a of I, right? So when I fix my j, that is the maximum value between these three, and a of k should be less than this and greater than a of I. So a of k should be, what is the let's say most favorable element, right, from the position j plus 1 to the position n, which could hold this? Well, is the maximum value which is less than a of j, right? So it should be less than a of j, but in order to be greater than a of I, the best candidate is the maximum value. So a of k should be the maximum value from this range, from the range from j plus 1 all the way to position n, right, which is less than a of j. And that's perfect, guys. That's what we want. We want to find out if there is some k, right? Again, the maximum value from j plus 1 and n, which is less than a of j. So we need to find this value really quick in big O of 1. Now, what is the difference between this and what we had to find at brute force approach number 2? In the brute force approach number 2, we had to find the minimum value from some prefix, right? Now, we have to find the maximum value from some suffix, right? Because it's from some position all the way to n, to the end of the array, but the maximum value which is less than some given value. So it's not enough just to compute a partial maximum on suffixes or something like that. We need something stronger. And that something stronger is the stack, right? And how will we use the stack? Well, we will go with our j. We are going to iterate from the end of the array all the way to the beginning. And why is that? Because when we are at some j, we will have already iterate through the elements on his right, which are our possible maximum value, our possible case, right? So I am going to go with this j, starting from position n, all the way to position 1 and j minus minus. And here we have actually two possibilities, because we could either use a set, right? Remember what is a set? A set is a collection which stores our elements increasingly or decreasingly sorted. So if we store a set here, we basically have iterated through all the elements between j plus 1, position j plus 1 and n. We basically added each element in our set, right? So when iterating for an element, inserting it into our set, the set is increasingly sorted and we can perform lower and upper bound on this set. So with the lower and upper bound, we can binary search basically the first greater element or the last less or equal element from that set, which is perfect because it solves our problem, right? The maximum value, which is less than a of j. So if our set is increasingly sorted and we perform a lower bound on a of j, and then we decrement one time that iterator, we are going to have the maximum value, which is strictly less than a of j. So a possible solution, basically I can write here a brute force approach, right? So this is, it's not actually a brute force approach because it's super good in time, but just for the fun of it, let's say it's a brute force approach because we are better than that, right? So in big O of n log n, right? Using a set, we have this third brute force approach. Now, the beauty of this solution, of the big O of n optimal solution, is that we can get rid of the set too, using the stack. And follow me. As you might know, if you have some experience with stacks, when using a stack, we will basically have some elements into the stack sorted either increasingly or decreasingly, right? So what should be the order of our elements in our stack here? Well, we need all the elements which are less than a of j. So when we are at some element, I need to iterate in my stack all the elements less than me. So we are going to have a stack non-increasingly sorted, right? Non-increasingly, hope my English is good, sorted, right? Because if we have our stack non-increasingly sorted, all right, let's suppose it's 10, 6, 5, 2, 3, 3 again, and 1. When we have some value, let's say when we are at the step aj equals 7, we are iterating from the top of the stack, right? Always we are taking elements from the top of the stack, and those elements are going to be less than my 7. If it was increasingly sorted, I would have started with the maximum, so I wouldn't covered my less elements, right, from the stack. So we are keeping a stack which is sorted decreasingly or non-increasingly, right? And each time we are in some position j and we want to insert that element in our stack, first of all, in order to maintain this stack in the non-increasingly sorted order, we have to get rid of those elements from the top which are less than my value. So we are basically iterating through all the elements less than me. We are going to try out each of these elements, right? So we are going to encounter at some point the maximum, right, from that stack, which is awesome. And we are going to pop those from the stack and then add my element. So here I will have 1, 3, 3, 5, and 6. Try each of those to be my possible k. If one of them is, so it's basically, I know that it's now less than aj. I should check if these elements are greater than ai. If I find one, return true. If not, I will just continue my algorithm. These elements are now gone from my stack and I add my 7 and continue the algorithm, right? Now, why is the complexity of this big O of n? Because you should know this. In a stack, of course, at some point we are going to remove more than one element, right? So you might think that, oh, this thing isn't big O of n squared because we have n elements, and for each element before inserting it to the stack, we are popping a lot of elements. And it's not. Because in some stack, if you think about it, each element is inserted and popped from the stack exactly once. And we have in our array n elements, right? So n elements plus 2 operations, one insertion and one removal is big O of n. Make sense? Now, we have the optimal solution. Let's jump into LeetCode and write the code for it. By the way, LeetCode is an amazing platform, the perfect one for preparing for technical interviews, right? So make sure you check it out. Now, for implementing this, we have an argument which is a vector of integer nums, and I am going to use my stack, so stack of integers st, let's say. In this stack, I'm not going to hold my elements, right, their values. I am going to hold positions, right? So basically here is the positions of my non-increasingly sorted elements. Right, perfect. Now, the main for loop, which we said is going to be for the j. So with the j starting at position, so we are here in nums. All right, first things first, we should compute that min val array, right? This is super important. So for the sake of this example, I am even going to use the vectors because it's the way to do it. So vector of integer max, no, it's min val, right? We are computing minimums. So min val of, first of all, let's take into a variable the size of the nums vector. So n equals nums.size, right? Now we have the size of this vector nums, and after getting the size, we are going to compute the min val. So let's just define it. Min val is going to be an array consisting of n elements, right? And each of those, I don't know, they don't have initially some value, right? So this is basically a constructor, right? Here with this n, I am constructing a vector of integers which has initially already n elements, right? Perfect. Now, let's compute the min val vector. And first of all, the min val on position 0 is going to be the element on position 0 from nums. So min val of 0 is nums 0. Then I will make a for loop starting at position 1 less than n, right? Because vectors are 0 indexed, super important, I++, and min val of I is going to be the minimum between min val of I minus 1 and nums of I, right? Perfect. Now, we have this min val. It's time to write our main for loop. And I am iterating from the last element, which here is n minus 1, all the way to position 1, right? Because j is the second one, so I can't go to position 0. And j minus minus. So I know the j. Now, I know the value of ai, because ai is always going to be min val of j minus 1. And I shall find my most favorable k, which I will find it in the stack. But first of all, stack is non-increasingly. I need to push this element, right? Each element of the array will be inserted to the stack at some point. So I need to insert now this element, but in order to keep it non-increasingly sorted, I need to pop those elements from the stack which are less than me. So while the stack is not empty, so not stack.empty, and I will go to stack.pop. Remember, here I have positions, not values. So for the value, I shall look at nums of stack.top, and while this value is how? Is less than my value, nums of j, right? What shall I do? Well, first of all, this could be a possible k. So I shall check if nums of st.top, so this a of k, is how? Greater than a of I, right? So if this is greater than my a of I, which I know is min val of j minus 1, right? Perfect. I return true right away. I have found my solution. If not, what shall I do? I remove that position from my stack. Perfect. Now, after this while loop finishes execution, I will insert my element in my stack. So stack.push, remember those are positions, so I insert here j, not nums of j, right? So I have basically all that I need. So after this for loop finishes execution, all right, here I should just return false, right? So fix the second element, which is j. We know what's the first element, and we try from the stack the possible third element. In the end, we just return false, and that's it. Let's run the code. Fingers crossed. Run code result. Let's see. All right. Passes the test cases, and now let's submit our solution. Fingers crossed again. I've already solved this task 2 months ago. All right, and I have a runtime error. Oh, this is a corner case. Be very careful, yeah. In interviews, you will be asked a lot of corner cases, right? So the interviewer will ask you, okay, think about some corner cases where you think your algorithm would crash, right? Or won't work, won't give the right answer. And you should be very careful of this one. One of these is always the empty array, right? Very popular on LeetCode. Almost every problem has this corner case. So how do we check this? Well, if nums.empty, if this array is empty, what shall I return? I return false right away because obviously I won't have a solution. So let's submit this again. Fingers crossed again. Hope for the best. And we are accepted, right? Perfect, guys. This was the problem. First problem that we have solved using the stack, and there are yet more to come. And notice how beautiful this is because we had 3 brute force approaches, right? N cube, n squared, then n log n, which is still a brute force approach, and then getting to the stack in the linear time solution. And remember, guys, if you really like the content and enjoy seeing me approaching these problems, walking you through my thinking process and writing the code together with me, don't forget to really support the channel. Hit that subscribe button, hit the like button, share it with your friends and everyone which would really find it valuable. And as always, guys, I will see you in day 4. Keep the hustle, and out.